right, so I suppose we can start. So welcome everybody for a second in-person seminar for the Cardiff analysis series to this stuff. And welcome to all of those who are following us. So hopefully they can really hear us better. So we would like to have Wilhelm Klingenberg from Durham University. So it's grateful for him to be here. So we came all the way to Durham. Thanks for accepting your invitation. He will talk about graphical mean curvature flow in R3.
Well, that's just the first chapter. The first chapter.
First chapter. So, and everything else will be revealed in due course.
Yes.
So, thank you very much again for being here and take it away.
Thank you very much. Thank you for inviting me. Thank the organizers. It's very nice to be here. And let me first give you the equation for graphical mean curvature flow for a function of two variables, x1, x2, in a subset of the plane cross non-negative time into R. And the equation very explicitly looks like this: d over du over dt equals Laplace u minus sum I j equal 1 to 2 u xi u xj over 1 plus norm gradient u squared, and here second derivatives, further second derivatives ui uj, and we will be looking for a situation where this first term dominates for this to be a strictly parabolic initial value problem and boundary value problems. So we impose, so this is d here cross r plus. Then for d cross 0, we impose a function, given function u 0, and for u along the boundary cross r plus, we impose values phi on the boundary of this domain. Let this denote the domain in the plane. Then the graph of that with boundary values phi will flow by this right-hand side, which stands for the mean curvature of the graph in ambient space. We'll get to that later. Let me first, so this is a quasi-linear. The coefficients here depend on lower order derivatives. So that's a quasi-linear parabolic problem. And here is a situation under which this problem 1 admits a solution and admits convergence. Namely, assume that for all planes in the graph space in R3 that intersect the loop graph phi in 3 points. So the graph here of phi on the boundary of the domain, as I say, is a loop. Assume that for any 3 points on the loop, the affine plane in R3, any affine plane that intersects those 3 points has slope bounded a priori by a number a. So here's the picture. Now let me try to d phi any 3 points this plane here should have slopes bounded for any choice of 3 points. So some discrete slope of the boundary condition. We impose that. Please note that this certainly excludes 3 points on this loop to lie on one line, because you could, yes, you could then have planes that are very small. So there's some convexity in here in addition to just bounded slope. It can be more, at least 3 points. Yes. Yes, that's a good point. So then the theorem is the following that we make reference to. Goes back to Bernstein and the solution of the plateau problem, which says that assume 1 and 2. Then, well, 2 items. First, the gradient of the solution with these boundary values for as long as it exists. So let's say plus is bounded by that same number. Secondly, the limit exists. This is indeed exists for all time. And the limit t goes to infinity of, say, the graph of our function u dot comma t exists and is a minimal surface in R3 with boundary in the loop phi. Minimal surface. So it's a stationary point compared to competing surfaces with the same boundary for the associated area coming from R3. So this is motivation for our theorem that we'll now get. So in a sense of, if you wish, so the limit would be this. Yes, A of, yes, schematically speaking. Yes, theorem. Now, we're about to give you a theorem that applies not to real valued functions, but to complex valued functions of 2 real or equally 1 complex variable. The gist will be, for such correctly defined evolution problem with good boundary conditions, the limit will be holomorphic, which is a particular case, of course, of the components being harmonic. Okay, here's the space in which that we propose to do this, that we have. So, namely, the space of rays in R3. So let L be such an oriented line in R3. Looks like this. So rather than points in R3, we will look to the space of rays in R3. Oriented lines. If this is the origin, and this is the unit sphere, then we can associate to this line the unit spanning direction of that line, concordant orientation, and indeed a vector in R3, if you wish, parallel transposed, that gives the orthogonal distance to the origin of that line. So this is now a pair here. So we have here, first of all, this projection from the space of lines to these pairs of vectors, and all other, the observation here, which other lines project to the same direction? Well, there will be other parallel lines, which, however, correspond to different perpendicular directions to the origin. So this is, in fact, equal to PL perp in R3, which is can maybe identified with at every point with the complex line, because we can rotate here about a line, and then we have an induced rotation on this plane, giving an identification of the perpendicular distance of a line with C. The upshot here is that this collection of all lines is the space TS2 of all tangent vectors to all points of the round two-sphere. So rather than considering surfaces in R3, we consider surfaces in this space. Now, crucially, we have a distance on this space, a metric, if you wish. And the distance is as follows. It's a signed distance. And that's an angular momentum. The signed angular momentum is a function delta of one line to another line, and it is given by this distance vector from one to the other in absolute value times the sine of the angle of pi L1, pi L2. So what is this distance here? Given two lines, let's choose one this way and one this way. This is L1, this is L2. Do you agree there is a unique perpendicular vector that's perpendicular to both of them from one to the other? And that will be, we'll take the Euclidean length of that vector here. Do you agree that by parallel translation of L1 to the tip of this, we have here an angle in the plane generated by these two now translated joining lines from L1 to L2? That's this angle here. So this is a function of two variables on this space. It's signed. The momentum, the angular momentum, you see, that's it tells you how much L2 rotates about L1. Moving from L2 to L1 is a rotation, is a movement. So in fact, it's a well-known function in mechanics. And what we now propose is to consider a mean curvature flow in this space. The mean curvature flow will also act on certain graphs, but let me first give you, before the graphical property, let me just tell you these will be space-like surfaces. So I'll continue here. So what we will now consider, the object of what we'll consider is a space-like surface. F2, if you wish, 2 dimensions in TS2. So this says we're looking at a surface of lines such that the rotational moments, the angular momentum between any two pairs of lines on this has a sign, is a positive. Space-like stands for positive. So for any L1, L2 in here, lying in here, this shall be positive. And those will be space-like lines, and that having such a surface in this 4-dimensional space is equivalent to clearly this function pi being injective. You see, you wouldn't want to have two equal here because then the angle is 0. Can't have parallel lines in that surface. They wouldn't be rotating about one another. So this function pi on that surface is injective. And say if we have here a coordinate C with coordinate Z on there, then it will be the graph of a complex valued function in the fiber over S2 over the perpendicular directions, which we identified with C before. So such space-like surfaces will be F equals graph of small f. Of small f, where small f is at least locally a function from C to C, which corresponds to the function u, which was real variable here. It had a real variable here, and that stood for the graph in R3, for a surface in R3. So it is now for such surfaces that it is among such surfaces that we search for holomorphic surfaces, or equally holomorphic, represented by holomorphic functions f, small f. Let me then give the equation that corresponds to 1. Let me give that next. So this was theorem 3. Now we give equation 4. So that will be now the evolution equation. Okay, before I do that, let me just say that given that these are space-like surfaces, we can associate an area. Again, a signed area. Okay, for space-like, it'll be positive, but for any surface, it'll be signed. Signed area A of f will just be the integral over f of the associated 2 form that's associated to this distance. These are the things that you can invariantly integrate 2-dimensional submanifolds in a 4-dimensional space over. Now, for these space-like ones, this will be positive. Okay, we can put that here. Space-like. In general, it can vanish or it can be negative. Just like the angular momentum between one and another line could be 0, could be positive, could be negative. Here's now the system that replaces equation 1. df d over dt of this graph f on, now we're not considering a fixed domain, but a variable domain t in the plane. Okay, before it was fixed, now it's variable. That gives more freedom. So if you wish, okay. So, and I will not give now the right-hand side as before, but I'll say this will be, it's a variational problem. It'll be the L2 gradient of this area functional. So we're deforming f in that direction. That gives a maximal increase due to the signs in this situation of the area functional when deforming it into that tangent direction. So this now links problem 4. There's an equal formulation of problem 1 as this, exactly the same. This differential equation was a pointwise form of this condition, of the variational condition that we're deforming in the sign of steepest decrease of the area function. The boundary condition that we have here is initially cross 0 is an initial function. Initial condition, Now things become more interesting. F on the boundary of this moving domain cross R plus T is contained in some initial surface. Rather than prescribing the value on a fixed boundary, we're asking the boundary to be contained on the variable in some given fixed surface, where this is some given fixed surface. And finally, we have two further first order conditions, namely that the angle along the boundary for all time between the moving surface Ft and this boundary surface Ft is constant. That's like a Neumann condition, first order. So for second order problem, we're imposing here a problem on the first derivatives on the boundary for all time. And there's given, so if you count functions, free functions, there's one more condition that can be imposed, and that will be that the Cauchy-Riemann equation, d over dz, of this boundary function, of this moving function, f, at the boundary, del dt cross r plus t, is a prescribed value that goes to 0 as t goes to infinity. So this is the constant angle condition, and this is another first order condition that forces the boundary slope to become holomorphic as t goes to infinity. This vanishing is just the Cauchy-Riemann equation for f. So here's the picture. May I put that here? C, 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 Z. That was a subset of the two sphere. And here's now the perpendicular distance, which also corresponds to C. We're given an F tilde surface, which we will impose to be positive. That's a fixed surface that encodes the free boundary condition. Then we have here the moving surface in time over a domain dt, the graph of which is f, and we're imposing that angle here between this moving boundary and the fixed boundary is constant. This is an angle between two planes in R4. But these planes are both space-like in terms of this metric, and they intersect the line. So there's a geometry in R4 that lets you measure the angle in respect of this distance metric between two such planes. And in addition, we're imposing that this function f becomes holomorphic at infinity, which is like one partial derivatives in respect of z bar being 0. So that's the imposition that this plane here becomes a complex line as t goes to infinity at the intersection of this flow. So this larger system now takes place for mean curvature. In fact, it is equal to the mean curvature flow of a space-like graphical surface in TS2, where mean curvature flow and graphicality is in reference to this angular momentum. We had 2 boundary conditions before for the U. Here we have 4. You see, this imposition here are 2 boundary conditions because we're asking this value of f to lie in a codimension 2 surface in R4. So that's two real conditions. This is a real condition, and that's a real condition. So we have two Dirichlet and two Neumann problem for this variable domain for a complex function that takes place for one Dirichlet and one Dirichlet problem for a fixed domain in codimension 1. So this happens to all work out, and I will now just give you the estimates that make this work. Okay? Are there any questions here? So again, this is a very particular geometry of 4 dimensions. However, it's not more particular than Euclidean geometry. 2, 2. 2, 2. Yes. I'm not giving out geometric terms what this metric is. I just gave it physically. So yes, it's 2, 2. What I'm saying is that this 2, 2 metric is as natural as the Euclidean metric. Because rotational angular momentum, it derives from Euclidean distance and from orthogonality. In fact, it can be shown that the isometries of TS2 that preserve this metric are just the isometries of R3. So this metric is equally rigid, it nails down the same. However, it operates on a larger space with more freedom. We say here this freedom is enough to generate an object as elusive as a holomorphic function. Theorem 5. Now, the estimates this is all collaboration with Brendan Guilfoyle. First point is now a C0 estimate. Namely, this surface, this family of surfaces is contained, there exists a compact subset in TS2. Please note TS2 minus a point here. This is non-compact manifold. So this says this moving surface will not move out to infinity on S2. It'll stay away like from the North Pole. So this domain won't become infinitely big. And also in the fiber, it's bounded. So it's not going to be move too far away from the origin as lines. They won't tilt too far away from the initial ones. That's on S2. And they won't go R too far. It's some C0 estimate, some boundedness of the flow, some a priori boundedness. Of course, the point will be they will be extracted from these initial conditions. Second, I'm skipping some now, the mean curvature, which is just, in fact, this gradient, this vector here, also denoted by H of Ft in this metric defined by D for all times and all domains is bounded, depending on B, C boundary values and capital K as established here. So these are some of the second derivatives. As before, it was a Laplace, it was a certain combination of second derivatives. That's not all parts of second derivatives, but this combination, which is just the length of this vector here. So this is the speed at which we move here is also bounded. Not only the space, but also in which you're moving, but also the speed. Then, given this, we have the crucial one, which is that the gradient of f forever, as as a graph is bounded. Depending on the previous estimates. Now, please note, having such a thing tells you this is a strictly parabolic problem. And now I may have erased the original problem here. It was when the first derivative, this A, this constant A that bounded the first derivatives of U, that's bounded by 100. That will give that these terms that were added to it would be strictly smaller than 1. So that here, Laplace plus other second derivatives with a constant smaller than 1. So that tells you Laplace dominates, strictly parabolic. Same here. That's the nature of these quasi-linear equations. This gives, as before, strict or uniform parabolicity of this problem. What was it? 4. Okay. Okay. Now I'll just then once we have this, we prove that in fact there is a sequential convergence, not as t goes infinity, but there is a sequence of times going to infinity for which the limit of f is indeed holomorphic. Next bullet point, didn't fit there anymore. Limit, there exists a sequence of times. J goes to infinity. Say the surfaces, ftj. These will all be surfaces with boundary ts2, comma f tilde. That's the fixed boundary, is holomorphic. Well, what does that say? That says that the Cauchy-Riemann equation for f infinity. Bar, that's Cauchy-Riemann, for d infinity cross infinity is 0. That's just saying that the graph of a holomorphic function is a holomorphic curve. Finally, in this, these surfaces are particular maximal surfaces, not minimal surfaces. So from the fact that, as Julian pointed out, that this is an indefinite metric, this variation problem increase rather than decrease area. And that's in fact a good thing as far as these estimates is concerned. That helps. So this is a maximal surface. And is a maximal surface. In TS2 in respect of this distance. So these are surfaces that have angular momentum in a maximal fashion. So think of these as, think of a uncooked spaghetti. Take them out of the bag and twist them. They open up. What is maximal? If they become a hemisphere, because then they run into each other. They're oriented. As you become maximal, you have a full hemisphere spreading out, 2 lines of opposite direction. That's sort of, there's a repulsion there. I'm not saying that d infinity is the hemisphere. It'll be a subset, depending, but non-empty, an open subset, depending on the epsilon and the alphas and so on. So there's not much explicit control that we have on the domain. But it's a good domain, it's an open connected subset. And the boundary values are whatever these are on that boundary. The angle is lost. There's no convergence in C1. This convergence is only C0 up to the boundary. That will be, in fact, overdetermined for holomorphic to also preserve the angle. But it's beautiful how the estimates just show that C1 convergence only happens in the interior, not up to the boundary, but there's C0, C1, as C0, there is up to the boundary. So the boundary conditions are preserved. Let me now give an indication of how to prove these estimates. TS2, delta. That's called a maximally twisting surface. So it's a surface of rays that have maximal angular momentum for pairs. So this is angular momentum. It's not parallel and it's not intersecting, but they skew. So a maximally skew. Yes, yes, yes. Well, yes, yes, yes. Competitors have an inequality. Yes, exactly. Critical point, and there's an inequality for competitors in first order, in variation, in derivative. Exactly. Weakly, smaller or equal. Yes. So what does this result tell you? It tells you that if you take the tangent bundle of S2 and you take some section or some space, F0, and you choose an angle, beta, and a constant C, and an initial surface, that's space-like. Yes? Then there will exist some domain D infinity over which there exists a holomorphic function with boundary in there. That's a statement. Okay, so here's now, so I'll just indicate just maximum usage, which is a standard method in variational problems. For some of these ingredients. So let me formulate that. Okay, first of all, we have two functions. Will you agree that we have on lines L, this is a point in TS2, the real number, this is now a positive real number, R squared, which is just the orthogonal distance to the origin. That's a real function, non-negative, on all lines. It'll be 0 if this line passes to the origin, otherwise it's a positive number, R squared. Secondly, we have, now we will need a metric to measure how far we are away from being maximal or holomorphic. Away from the North Pole, we have here Z coordinate, and we have here the coordinate C, which is TZS2. And we have here our moving surface FT. On this moving surface, we have an induced metric. It's just the distance function on this FT. So G is just the distance not between any two, but between two lines corresponding to points on these surfaces. Okay, it's, yes. Yeah, so you by linearization, you get a differential geometric measurement, but I'll stay with this metric. Now, this graph is a function f of z, z bar, t. Do you agree that if a real differentiable function of a complex variable is a real differentiable variable of two complex ones, z, z bar? And the vanishing, it's not depending, the vanishing of this derivative is just Cauchy-Riemann. It's just a way to write a real differentiable complex valued function. And we now have, so this is Ft is a moving surface in TS2 with metric D. Now we have the following proposition, namely the distance, the maximal distance r squared on the surface is decreasing under the flow. That means the initial values give you how far it at most is this surface as far as lines in R3 goes from the origin. So proposition 6 goes, if you wish, the first step that we prove is that, okay, let now Laplace G be the Laplace operator on this surface in respect of this metric. So we have on this surface the Z1 equals Z formally and Z2 equals Z bar, two variables, two coordinates. And in respect of these coordinates, we have the metric Gij, which is the principle, the symbol of the Laplace operator associated to this metric. So this Laplace operator is just given by G inverse of that matrix del I del J, where 1 corresponds to Z and 2 to Z bar. This is the principal symbol of this gradient of the functors, just the Laplace operator for this distance. Then we have that the corresponding parabolic operator, d over dt minus Laplace G on the surface of the maximal distance, the distance function squared is or equal than 0. This says that the maximum of r squared on the surface Ft is decreasing. So this says that as far as you're initially, the surface will not move out further in terms of this distance r squared. And the other one is d over dt minus determinant of G. So this is a symmetric 2 by 2 matrix, Gij. Its determinant will tell you that this is a positive, definite metric, which is just saying it's space-like. Now, if we let this act minus Laplace G on the determinant on this real function, then this is greater or equal to 0. Well, we're starting initially with a space-like surface. And then this says, so the determinant initially is positive. And this says that the minimum of the determinant of the G on the flowing surface is increasing in time. So you're not going to become sort of a less space-like, that the surface is not, you're not going to develop sort of lines that are parallel or that are more parallel than before. This will spread. And it's quite obvious from the spaghetti example. If you twist more and more, the area spreads out more. And that's just this. So these are both maximum principle arguments so that are proved by computation. I can just give you one equation that comes about for the evolution. So what to prove this? I'll just give one more line here. Proof. Yeah. So you need some first derivatives, df bar over dz. So this is df over dz bar bar. And we need rho. That is a conformal factor times d over dz bar of u inverse squared f. So these are some slopes. You see, these are first derivatives of the graph function. Yes, first derivatives. Some combinations of first derivatives. So if you agree, if this one is 0, that means it will be holomorphic because this is the bar of the bar derivative. And this is some other sort of, in fact, there's a geometric interpretation for those. Then the induced metric can be written in terms of these first derivatives, of course. So it'll be I sigma minus imaginary rho minus imaginary rho minus I sigma bar. This is now the 2 by 2 matrix that tells you infinitesimal distances on this surface. And then you you take the determinant, or there's also an expression for R. You see, of course, which is sort of the length of the tangent vector. It tells you how far you are away from the origin. And you compute the evolution of these terms. So in particular, you have an evolution for f. Then, given this, then the evolution for f. That'll be the last item that I will give. Let me use a new blackboard to give you sort of an idea what these equations are that need to be computed. So now we're stopping with what we began the first part with. I gave in the beginning the equation for u, the derivatives. Now I'm doing it for f. How about that? We're coming a full circle. Okay, it is d over dt f equals Laplace. You remember that? Of u, f. Here you go. And then there were second derivatives. Well, here, this story looks like follows. I sigma bar determinant g inverse times u z sigma minus z bar rho bar plus f bar minus z f. So what's the difference here? What's the difference between this one and the first equation? No second derivatives here. Remember the second, pardon? Pardon? Yes. This minus. Yes. You see, you remember in the very beginning, there were second derivatives on the right. There was a Laplace u plus u xi xj with a factor that was smaller than 1 if we have a gradient estimate. Here, not. Of course, I'm lying. Yes, because this contains the first derivatives. See, this thing does. This thing is sort of these metric coefficients, of course. In fact, I gave it. They were first derivatives. What I'm saying is that this is the right geometric term by which expression by which to do this evolution and by which to control this flow. So this getting a holomorphic function, okay, is not an equation. Let me stop with this, but a system of equations. It's 2 equations for the real and imaginary part, rather than 1 just for u. Now, systems are infinitely more difficult than equations. And a holomorphic function is infinitely more rare than a harmonic function. They are harmonic, but they're also linked by Cauchy-Riemann. Of course, there's a reason why we did this. This theorem has, in fact, geometric and global applications in global analysis on numbers of umbilic points on certain embeddings of surfaces. However, it is, of course, absolutely interesting in its own right, because anytime you can construct a holomorphic function with some properties, it's interesting in itself. Thank you very much.
Questions for either online? The very first.
Yes. Yes.
So from the 3-point position, we get the gradient.
Yes.
Why isn't it enough to impose a gradient estimate as an initial condition? Why do you need this stronger 3-point condition?
It's the boundary condition.
Yeah, but what is that the gradient estimate for that?
Yes.
Why can't you just say the gradient is initially bounded? And then
It's a boundary value problem. Yeah. Can you, is there such a theorem? I don't know. I don't know. It's a question. I'm not sure. I don't think so. Because you need then slopes at the boundary. So, okay, there are several theorems of that type, many theorems. This that I gave for you, for the real function, is the version that is used to solve the plateau problem. So it will be pretty strong and big. Plateau problem is if you have a closed curve in R3, does it span a bubble, a soap disk? Yes, it does. We all know that, right? We pull it out. The mathematical proof of that, of course, is by Douglas and Rado, and they use this 3-point condition. It, however, goes back to Hilbert. So it's an ingenious thing. But there will be other conditions, absolutely. Yes. But I'm using it as a motivation for conditions of space likeness that I imposed. Yes? Yes. 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 But it's a very well-researched area. I mean, do you know such theorems for mean curvature flow with prescribed boundary?
yes,
And what do they impose?
well, they have a theory that normal.
Yes. Yes. And is there any condition on the boundary? Well, that take place for this 3-point condition. They must have some condition on the boundary or not. What is it?
Depends on the problem. You could impose Dirichlet condition and normal.
Well, I did Dirichlet condition. Yes. And what's then the condition on the Dirichlet boundary values in that classical theory? That's all? Yes. Yes. Well, but it needs to be convex, the domain. It's not, okay, but that's all enclosed in here. Convexity was enclosed in here of the domain. Yes, yes, yes. And also tells you something about the slope. So both tells you something both about the domain and the slope of the function. Of course, the function is related to the boundary of the domain, sort of. It's a convexity. And if convexity was at the heart of what we do as well, because space likeness is convexity, quote unquote, for lines, is twisting, is angular momentum for lines. And that's where theorem 1 and last theorem come together.
Yeah, so apparently this is the only microphone that they can hear. So any more questions for Wilhelm from, so Michael.
Hi, I'm afraid I'm a bit poorly equipped to understand the whole thing. I mean, I understood you started from surfaces, right? They look at the evolution of a surface. Then you jump to that space, and then I understand there was a tangent bundle, right?
Yes.
And then you jump to that space, and I didn't get that connection.
The whole point, all you need to get from that is we're jumping from R3 to R4.
And what is that R4? This is what I want.
R4 is a subset of all rays in our array.
Yeah, but how are they connected to?
That's this picture that I tried to give here of direction and orthogonal distance. That's this picture of direction and orthogonal that I gave in the second blackboard.
I think that all these traits are related to the surface U.
Surface U? They're not. Well, I didn't make a claim to that effect.
Oh.
I didn't. Well, you can consider rays that are perpendicular to the surface U, but I didn't do that.
Oh, okay.
Yeah.
So there was
No, okay. As far as my talk is concerned, there's no connection. However, as far as mathematics is concerned, there is a connection, but I didn't speak about it.
Oh,
So,
you just considered another
yes,
surface
yes, yes,
surface in that
yes,
four-dimensional
yes,
space.
yes.
So
However,
I-
it's a very good question. It's a better question than you may think. Because you see, a surface in R3 gives rise to an F. Will you agree that this is a surface in R3 for the moment? Take all these lines.
Yeah.
Is that an F? Is that a two-dimensional family of, yeah. So there is,
Okay.
yes.
This is the.
No, it's not. It's more complicated. I didn't speak about that, sorry. So I omitted geometric aspects of the story in favor of the equation of like analytic sort of method and easy. No, it is. Yes, this is not the F, but a deformation, a twisting of it. Yeah. I'm sorry. So it's a very good question. And so your question leads, in fact, to the full motivation of what we did. We cut it off because we're speaking only 50 minutes. But the fact that you noticed this shows that I guess I was successful. Yes, you're right. This is not F yet. It's not. That's the point. You would still have to twist them a little bit. These surface will be null. That the surface of these lines are all parallel or intersect. They have null distance. So they're no good for the second problem. But you can twist them. You can give them a little bit, and then you can do the.
Is it now in 3D like?
Yes, it's like the rays through the origin in R3, right? That's an F. But this F has zero surface because all these F pass through the origin and they don't rotate about one another. So they are no good in terms of this evolution because we are doing space-like twisting. However, there is a passage that will be a second chapter. Yes. The question is how this came about.
Yeah.
But then finding holomorphic function is interesting.
Any more questions from here? From any questions from our online audience? Let me check. No, it doesn't look like the case. So let's give a round of applause to Wilhelm again, thanking him for the very nice talk, both physical and virtual. So thank you very much.